The Dapr Way, Mastering Distributed Application Runtime. 1. The Distributed Challenge. Why Dapr? In the dynamic landscape of modern software development, applications are rarely static. They grow, they scale, and they evolve to meet ever-changing user demands and business needs. For many years, the standard approach to building software was the monolithic application, a single, self-contained codebase, often deployed as a single executable, managing everything from user interfaces to data storage and complex business logic. This approach offered a deceptive simplicity in its early stages. Development was straightforward, testing often happened within a single environment, and deployment meant pushing one package. The monolith's plight, why we moved away. While the monolithic structure served its purpose for smaller-scale projects, its limitations became painfully apparent as systems grew in size and complexity. Imagine a grand, intricate clockwork mechanism where every gear and lever is interconnected. If one tiny piece malfunctions, the entire mechanism can grind to a halt. Similarly, in a monolith, scaling became a Herculean task. To handle more users or more data, you often had to scale the entire application, even if only a small component of it was under heavy load. This was akin to buying a new, larger house just because you needed more space in the kitchen. Team velocity stalled. As more developers joined, the single codebase became a bottleneck. Merge conflicts were rampant, changes in one area could inadvertently break another, and the sheer cognitive load of understanding the entire system significantly slowed down development and release cycles. Technology upgrades were nightmares. When a new framework or programming language emerged that promised significant improvements, migrating a monolithic application to it was often a costly, risky, and time-consuming rewrite, effectively preventing innovation. A single point of failure. A bug in an obscure module, a memory leak, or a performance issue in one service could bring down the entire application, impacting all users and business functions. The resilience of the system was only as strong as its weakest link. These challenges led the industry to seek alternative architectures, paving the way for the rise of distributed systems, most notably through the microservices paradigm. Embracing microservices, the promise and the pitfalls. Microservices promised liberation from the monolithic constraints. The idea was elegantly simple. Break down the large, monolithic application into a collection of small, independent services, each responsible for a specific business capability. These services could be developed, deployed, and scaled independently, communicating with each other over a network. The benefits were compelling and quickly became evident. Independent deployment. Teams could deploy new versions of their services without impacting or waiting for other teams, accelerating release cycles. Targeted scalability. If your user authentication service was under heavy load, you could scale solely that service instead of the entire application, leading to more efficient resource utilization. Enhanced resilience. A failure in one microservice would ideally be isolated, preventing a cascading failure that brings down the entire system. Technology diversity, polyglot. Teams could choose the best programming language, database, and frameworks for their specific service, fostering innovation and optimal performance. However, as organizations began to adopt microservices, a new set of complexities emerged. The monolith was a big ball of mud. Metaphor was replaced by the distributed monolith, or, more accurately, a distributed bag of plumbing. While developers gained flexibility, they suddenly found themselves grappling with an entirely different set of challenges. The distributed plumbing problem, a shared burden. The freedom and flexibility of microservices came with a significant cost. The inherent complexities of distributed systems, once hidden within a single codebase, were now exposed and amplified. Developers, previously focused on writing business logic, found themselves spending an inordinate amount of time on what can be described as distributed plumbing. How do services find each other? In a monolith, functions simply call each other. In microservices, you need service discovery mechanisms to locate other services across a network. How do services talk securely and reliably? Network calls are inherently unreliable. Developers had to implement complex retry logic, circuit breakers, to prevent cascading failures, and ensure secure communication with proper authentication and authorization. How is data managed across services? Ensuring data consistency across multiple databases owned by different services became a significant challenge, often requiring complex strategies like eventual consistency or orchestrating distributed transactions. How do we handle events and asynchronous communication? For event-driven architectures, developers needed to integrate with message brokers, handle subscriptions, and ensure message delivery guarantees. How are secrets handled? Hard-coding API keys or database credentials was no longer an option. Securely managing and injecting secrets into services became critical. How do we debug a distributed system? When a request spans multiple services, tracing its journey, collecting logs, and aggregating metrics from disparate sources became a daunting task. The proliferation of libraries and SDKs. Each programming language or framework required its own set of libraries to handle these distributed concerns. This often led to inconsistent implementations across different teams and technologies, creating what we call polyglot fragmentation. This distributed plumbing meant that every team, regardless of its specific business domain, was constantly reinventing the wheel. The focus shifted from writing innovative business capabilities to boilerplate code for infrastructure concerns. Not only was this inefficient, but it also introduced subtle bugs and inconsistencies that impacted reliability and security. Furthermore, excessive reliance on specific cloud provider software development kits or proprietary libraries for these concerns often led to vendor lock-in, making it difficult to migrate applications to different environments or cloud providers without significant rewrites. The dream of microservices, agile teams, independent deployments, and technological freedom was often overshadowed by the relentless burden of managing these pervasive distributed system complexities. Clearly, a better way was needed. Introducing Dapr, your distributed application runtime. Enter Dapr, the distributed application runtime. Dapr was created as a solution to precisely this dilemma. Its core premise is to externalize the common, repetitive, and complex aspects of building distributed applications, allowing developers to focus on the truly valuable part of their work, the business logic. Imagine Dapr as a universal set of utility services that run alongside your application. When your application needs to do something that involves a distributed system, pattern, perhaps call another service, save some state, or publish an event, it doesn't try to handle those complexities itself. Instead, it makes a simple, standard request to Dapr. Dapr then takes care of all the underlying intricacies, regardless of the technology stack involved. This unique approach is facilitated by Dapr's sidecar pattern. Think of it like this. Your application runs in one container, and right next to it, sharing its network and context, is another container running the Dapr runtime. This Dapr sidecar exposes a simple, language-agnostic application programming interface, accessible via standard HTTP or gRPC calls. This means your application, written in any language, whether it's Python, Java, Net, Go, or anything else, can talk to Dapr using familiar network protocols. Dapr provides a collection of building blocks, each addressing a specific capability common in distributed systems. Service invocation, for reliable and secure communication between services with built-in retries and tracing. State management, for storing and retrieving application data, allowing you to use different state stores without changing code. Publish-subscribe, for building event-driven architectures, letting you send and receive events through various message brokers. Resource bindings and triggers, for integrating your application with external systems like databases, message queues, file systems, or cloud services. Secret management, for securely accessing sensitive information like API keys or database credentials. Actors, for building scalable, stateful, and fault-tolerant services based on the actor model. Observability, for generating metrics, traces, and logs that provide deep insights into your distributed application's behavior. Configuration, for managing dynamic application settings. By providing these standard building blocks, Dapr tackles the distributed plumbing problem head-on. Polyglot, Because Dapr exposes a standard HTTP gRPC API, it truly supports any programming language, allowing teams to choose the best tool for the job without incurring complexity. Portability. Each Dapr building block can be configured to use different underlying infrastructure components, often with just a simple configuration change. For example, you can use Redis for state management in development, then switch to Azure Cosmos DB or Amazon DynamoDB in production without touching your application code. This dramatically reduces vendor lock-in and fosters true application portability across cloud and on-premises environments. Productivity. Developers are freed from the burden of repeatedly implementing complex distributed system patterns. They can focus their time and energy on writing unique business logic, accelerating development cycles and innovation. Consistency. Dapr ensures that common patterns like retries, circuit breakers, and observability are implemented consistently across all services, leading to more resilient and maintainable applications. In essence, Dapr acts as a middleware layer, abstracting away the inherent complexities of distributed systems, much like an operating system abstracts away hardware complexities from applications. It allows developers to write once, run anywhere in the distributed world, focusing on what matters most, delivering business value. Who should read this book? This book is for anyone navigating the intricate world of distributed systems and microservices. Software developers. If you're building applications with microservices and find yourself struggling with the plumbing code, or if you're new to distributed systems and want a simpler way to get started, you'll learn how to leverage Dapr's building blocks to write cleaner, more resilient, and portable code. Solution architects. If you're designing modern application architectures and seeking ways to standardize development patterns, improve resilience, and ensure future portability across environments, you'll gain a deeper understanding of how Dapr fits into the broader ecosystem. Operations engineers, DevOps, SREs. If you're responsible for deploying, managing, and monitoring distributed applications, you'll learn how Dapr integrates with container orchestrators like Kubernetes, its operational aspects, and how it simplifies observability. By the end of this book, you will not only understand what Dapr is, but also have the practical skills and conceptual clarity to confidently adopt and leverage Dapr in your projects, transforming the way you build and manage distributed applications. Let's begin the journey of mastering Dapr. 2. Understanding Dapr, core concepts and architecture. In the previous chapter, we explored the complexities inherent in building and managing distributed applications, and how Dapr emerges as a powerful solution to these challenges. Now, let's peel back the layers and examine the fundamental concepts and architectural design choices that make Dapr so effective. Understanding these core principles is crucial to fully leveraging Dapr's capabilities. 2.1 Dapr's unique approach, the sidecar pattern. At the heart of Dapr's design is the sidecar pattern. To understand this, imagine your application as a traveler in a foreign land. Instead of learning a dozen new languages or figuring out complex local customs all by yourself, you bring along a personal interpreter and guide. This guide sits right next to you, understands your wishes, and handles all communication, navigation, and local interactions on your behalf. Your guide is Dapr, and it literally runs alongside your application, acting as its dedicated distributed systems runtime. In more technical terms, the sidecar pattern involves running a separate, isolated process, the Dapr process, or Dapr runtime, alongside each instance of your application. When deploying in environments like Kubernetes, this often means the Dapr runtime runs in a separate container within the same pod as your application. Crucially, these two processes share the same network namespace, meaning they can communicate with each other over localhost, the self-same machine address. This seemingly simple architectural decision yields profound benefits. Language agnosticism. Your application doesn't need to know anything specific about Dapr beyond simple HTTP or gRPC calls over localhost. This means you can write your application logic in any programming language you choose: Python, Java, Net, Go, Node.js, C++, and many more, as long as it can make standard network requests. Dapr provides SDKs for popular languages to simplify these calls, but they are not strictly required. Application code isolation. Your application's codebase remains clean and focused on its core business logic. All the complex distributed systems, boilerplate like retries, circuit breakers, security, and integration with external infrastructure, is handled by the Dapr sidecar. This separation of concerns improves maintainability and reduces the cognitive load on developers. Abstracting infrastructure interaction. Your application expresses its intent to Dapr, e.g., save this state, publish this event. Dapr then translates this intent into the specific API calls and protocols required by the underlying infrastructure component, e.g., a Redis database, a Kafka message broker, an Azure Key Vault. This abstraction means your application doesn't need to directly integrate with these technologies. So, when your application needs to, say, invoke another service, it simply makes an HTTP or gRPC call to its local Dapr sidecar. The sidecar then takes responsibility for finding the target service, handling security, applying resilience policies, and routing the request. 2.2. The Dapr Runtime. Control plane and data plane in balance. Dapr is more than just a collection of sidecars. It operates with a clear separation of concerns, comprising both a data plane and a control plane, much like modern network architectures. The data plane consists of all the Dapr sidecar processes running alongside your applications. These are the workhorses that handle the actual traffic, executing the Dapr building block logic, e.g., performing service invocation, managing state, publishing messages. Each sidecar directly interacts with its associated application and the configured infrastructure components. The control plane is a set of system services that manage and support the operation of the Dapr data plane. In a Kubernetes environment, these control plane services run cluster-wide and are responsible for things like Dapr operator. This is the core component that manages Dapr custom resources, like Dapr component configurations, which we'll discuss shortly. It watches for changes to these configurations and ensures they are applied to the Dapr sidecars. Dapr Sentry, responsible for providing automatic mutual TLS or MTLS certificates. This ensures secure, encrypted, and mutually authenticated communication between all Dapr-enabled applications, out of the box, without any code changes in your application. Dapr Placement, a critical service, particularly for Dapr's actor building block and service invocation. It maintains an ordered list of Dapr-enabled applications and their associated IP addresses, allowing Dapr to correctly route requests and place actors across the cluster. Dapr Metrics gathers and exposes operational metrics from the Dapr sidecars, providing crucial observability data to monitoring systems. Together, the control plane ensures that your Dapr ecosystem is properly configured, secure, and discoverable, while the data plane handles the high-performance execution of distributed application patterns for your applications. This balanced architecture provides both management capabilities and robust runtime execution. 2.3. The Dapr Building Blocks, a toolkit for distributed systems capabilities. Dapr's power lies in its set of building blocks. These are standardized APIs that abstract away the complexities of common distributed systems capabilities. Each building block addresses a specific class of challenge, providing a consistent interface for developers regardless of the underlying technology. Here's an overview of the primary Dapr building blocks. Service invocation. This building block enables reliable and secure communication between services. Instead of your application directly calling another service over the network, it asks its Dapr sidecar to do so. Dapr handles service discovery, MTLS encryption, retries, and can even apply circuit breaker patterns, making cross-service communication resilient and secure with minimal effort from the developer. State management. Distributed applications often need to store and retrieve state reliably. The state management building block provides a consistent API for CRUD, create, read, update, delete operations on key-value pairs, abstracting various state stores like Redis, Azure Cosmos DB, AWS DynamoDB, or PostgreSQL. Your application simply says, save this state, and Dapr persists it to the configured state store, handling transactions and consistency models. Publish, subscribe, pub sub. For building event-driven architectures, the pub/sub building block allows services to publish messages to topics and subscribe to messages from topics through a uniform API. Dapr integrates with popular message brokers such as Kafka, RabbitMQ, Azure Service Bus, and AWS SNS SQS, abstracting away their specific client libraries and message formats. Resource bindings and triggers. This building block provides a standard way for your application to interact with external systems. Input bindings allow Dapr to trigger your application when an event occurs in an external system, e.g., a new message in a queue, a file uploaded to a storage blob, an incoming HTTP request. Output bindings allow your application to interact with external systems, e.g., sending an email, writing to a database, uploading a file by simply calling Dapr. Secret management. Handling sensitive information like database connection strings, API keys, or cloud credentials securely is paramount in distributed systems. The secret management building block provides a consistent API to retrieve secrets from configured secret stores like Kubernetes Secrets, Azure Key Vault, AWS Secrets Manager, or HashiCorp Vault. Your application requests a secret by name, and Dapr fetches it securely. Actors. Dapr includes an implementation of the virtual actor pattern. Actors are isolated, independent units of state and computation that communicate through messages. The actors building block simplifies the creation of highly concurrent, stateful services by managing actor lifecycle, placement, and concurrency, allowing developers to focus on the actor's behavior. Observability. Understanding the behavior of a distributed system is challenging. Dapr automatically integrates with OpenTelemetry and other telemetry systems to emit distributed traces, metrics, and logs for all Dapr-enabled applications and Dapr behaviors. This means out-of-the-box insight into how your services are communicating and performing, often without any application-level code required. Configuration. This relatively newer building block provides a way to retrieve and subscribe to application configuration from a Dapr-managed store. It allows for dynamic updates to configuration without requiring application restarts, facilitating agile deployments and operational flexibility. These building blocks act as a comprehensive toolkit, providing ready-made solutions for the most common distributed systems challenges, accessible through simple, consistent APIs. 2.4 Dapr components. The pluggable infrastructure layer. The truly powerful aspect of Dapr's building block design is its underlying component model. While a building block defines what a capability is, e.g., state management, a Dapr component defines how that capability is implemented using a specific underlying infrastructure resource. Consider the state management building block. You might need to store state. Dapr doesn't care where you store it. You, as the developer, simply call Dapr State Management API to save this state or get that state. It is through a component configuration that you tell Dapr which underlying state store to use. This could be Redis, or Azure Cosmos DB, or PostgreSQL, or even a local file system for development purposes. Dapr components are configured using simple YAML files. For example, a state component might be defined similarly to this. You'd specify the API version and kind as API version. Dapr.io/v1alpha1 and kind. Component, then provide metadata like a name for your component, e.g., my state store. Crucially, you declare the type of component, such as state.azure.cosmosdb or stateRedis, and then provide relevant connection details or authentication credentials within a metadata section. This pluggable component architecture provides immense flexibility. Infrastructure agnostic. Your application code is completely decoupled from the specific infrastructure used. This dramatically reduces vendor lock-in and allows seamless migration between different cloud providers or on-premises solutions. Ease of configuration. Switching infrastructure components is often as simple as changing a YAML file and restarting Dapr, or letting the Dapr operator apply the change in Kubernetes. No application code changes are required. Developer freedom. Teams can develop and test applications using lightweight, local components, like in-memory state stores or file-based message queues, and then easily transition to robust, production-grade cloud services or on-premises solutions simply by updating the Dapr component configuration. Dapr's comprehensive registry of officially supported components is constantly growing, enabling integration with a vast array of databases, message brokers, secret stores, and other ecosystem technologies. 2.5 Polyglot, portability, and productivity. Dapr's core tenets in action. The architectural choices we've discussed, the sidecar pattern, the building blocks, and the component model, coalesce to deliver Dapr's three core promises. Polyglot. As emphasized, Dapr's standardized HTTP gRPC APIs mean your applications can be written in any language. Dapr eliminates the need for language-specific libraries to interact with distributed systems plumbing, fostering true polyglot development across diverse teams within an organization. Portability. The component model ensures that your application code is environment-agnostic. You can develop locally with self-hosted Dapr, deploy to Kubernetes in your data center, and later move to a managed service in the cloud, like Azure Container Apps or AWS EKS, without altering your application code. This dramatically reduces friction for environment shifts and simplifies migration strategies. Productivity. By abstracting away the complexities of distributed systems, Dapr significantly boosts developer productivity. Developers spend less time writing boilerplate and integrating with disparate SDKs, and more time building innovative business features. The out-of-the-box resilience, security, and observability provided by Dapr also reduce the operational burden and mean less debugging time for distributed issues. In essence, Dapr acts as a powerful abstraction layer, separating your valuable business logic from the ever-present complexities of distributed infrastructure. 2.6 Chapter Summary and What's Next. In this chapter, we delved into the core architecture of Dapr. We explored the genius of the sidecar pattern as a language-agnostic intermediary. We understood the roles of the data plane, the Dapr sidecars doing the work, and the control plane, managing configuration and security. We were introduced to Dapr's powerful building blocks, each providing a standardized API for a common distributed systems problem, and saw how the component model enables unmatched flexibility and portability by allowing seamless swapping of underlying infrastructure. Together, these elements deliver Dapr's promises of polyglot support, portability, and enhanced developer productivity. With this foundational understanding of Dapr's concepts and architecture, you're ready to get your hands dirty. In the next chapter, we will walk you through the practical steps of installing Dapr and running your very first Dapr-enabled application. 3. Getting started with Dapr. Installation and your first application. Having explored the theoretical underpinnings of Dapr, its core concepts, and its architectural benefits, it's time to get practical. This chapter will guide you through the process of setting up your development environment, installing Dapr, and building a simple, hello world style distributed application. This hands-on experience will solidify your understanding of how Dapr works alongside your code. We will focus on Dapr's self-hosted mode, which is ideal for local development and testing. In this mode, Dapr runs as individual processes on your machine, separate from Kubernetes or other container orchestrators. 3.1 Setting up your development environment. Before diving into Dapr itself, ensure you have a few fundamental tools installed. These are common prerequisites for modern software development and will provide the foundation for running Dapr and your applications. Docker Desktop or Docker Engine. Dapr uses containers for its local components, like a default Redis instance for state and pubsub and a Zipkin instance for tracing. Having Docker installed and running is essential. You can download and install Docker Desktop from the official Docker website for your operating system, Windows, macOS. For Linux, ensure Docker Engine is installed. A code editor IDE. You'll need a text editor or integrated development environment, IDE, to write your application code. Popular choices include VS Code, IntelliJ IDEA, or Visual Studio. A command line interface, CLI. You'll be interacting with Dapr primarily through its command line tool. A standard terminal or command prompt like PowerShell, Windows Terminal, Bash, or macOS Terminal will suffice. 3.2 Installing the Dapr CLI and initializing Dapr. The Dapr command line interface, CLI, is your primary tool for managing Dapr. It allows you to install Dapr, run applications, check Dapr's status, and more. 1. Install the Dapr CLI. The installation process varies slightly by operating system. macOS, using Homebrew, open your terminal and type brew install Dapr/Dapr/Dapr. Windows, using PowerShell, open PowerShell as an administrator and type wget q https raw.githubuser-content.com/dapr/cli/master/install ps1 use basic parsing out file install ps1. Install ps1. Linux, using a script, open your terminal and type wget q https raw.githubuser-content.com/dapr/cli/master/install/install sh obin bash. After installation, verify that the Dapr CLI is correctly installed by running Dapr version. This command should return the installed Dapr CLI version. 2. Initialize Dapr in self-hosted mode. Once the CLI is installed, the next step is to initialize Dapr on your local machine. This command downloads and installs the necessary Dapr runtime binaries and sets up default components for local development. Open your terminal and execute Dapr init. When you run Dapr init, here's what happens. The Dapr CLI downloads the latest Dapr runtime, the Dapr binary, to your local machine. It starts 2 Docker containers, a Redis container. This is configured as the default state store and pub sub-broker for local Dapr applications. It's a lightweight way to get started with Dapr state management and pub sub building blocks. A Zipkin container. This is a distributed tracing system. Dapr automatically integrates with Zipkin to capture traces when running Dapr-enabled applications, giving you out-of-the-box observability. It creates default Dapr component configuration files, YAML files, in a Dapr directory within your user's home folder, e.g., /Dapr/components. These specify the Redis state store and pub sub-broker we just mentioned. You can verify that Dapr has initialized successfully by running Dapr status. This command should show that Dapr is running, with its runtime and supporting services OK. 3.3. Building your first Dapr application. The hello world of distributed systems. Let's create a classic client-server example to illustrate Dapr's service invocation capabilities. We will have 2 simple applications: a server application that exposes an endpoint and a client application that calls this endpoint. We'll describe the interaction verbally, as the specific programming language for these very simple applications is less important than how they communicate via Dapr. The server application, e.g., server app. Imagine a simple web server application. This application is written to listen for incoming HTTP requests on a specific port, say port 5000. It has a single endpoint, let's call it greetings, which, when invoked, simply returns a message like hello from Dapr-enabled server. Crucially, this server app has no direct Dapr code within it. It's just a standard web server. Its job is to listen for incoming HTTP requests and respond. As a Dapr-enabled application, it will receive incoming requests from its Dapr sidecar, meaning the path will generally start with something like v1.0 invoke. However, the app itself doesn't need to be aware of Dapr's specific API routing. It just needs to expose a standard HTTP endpoint. The client application, e.g., client app. Now, consider the client app. Its goal is to call the greetings endpoint on the server app. Without Dapr, the client app would need to know the server app's network address, handle retries if the server was busy, and ensure secure communication. With Dapr, the client app's interaction is dramatically simplified. Instead of making a direct network call to the server app, it makes a simple HTTP call to its local Dapr sidecar. This call is directed to HTTP localhost :30500. By default, Dapr's HTTP API listens on port 3500. The URL path it sends includes specific information for Dapr. The Dapr API version, typically v1.0. The invoke building block path, invoke. The application ID of the target service, e.g., server appid. The method name on the target service, e.g., greetings. So, the client app would construct a request that conceptually looks like this. Post http localhost :3500/v 1.0/invoke/server-app-id/method/greetings. It's important to note the http localhost :3500 part. When the client app is running with its Dapr sidecar, this localhost address refers to that sidecar. The client app doesn't need to know the actual network location of server app-id. Its Dapr sidecar handles all the service discovery, secure communication, and routing behind the scenes. Running Dapr with your applications, Dapr Run. To run your applications with Dapr, you use the Dapr Run command. This command launches your application and injects the Dapr sidecar alongside it. Let's assume you have compiled created executables for your server and client applications, e.g., server.exe and client.exe for simplicity, or simply Python serverpy and Python clientpy if using Python. Start the server application with Dapr. Open a new terminal for the server and run Dapr Run appid server appid at port 5000 Dapr HTTP port 3501 path to your server.exe. Let's break down these arguments. Appid server appid. This assigns a unique identifier, server appid, to your application. This ID is how other Dapr-enabled applications will find and invoke your server. At port 5000. This tells Dapr that your server application is listening on port 5000 for incoming HTTP requests. Dapr will forward requests to this port. Dapr HTTP port 3501. This specifies the port where this specific Dapr sidecar will listen for incoming HTTP requests from its companion application. Though the server application typically doesn't initiate calls to its sidecar for service invocation, it's good practice to assign a unique port if running multiple Dapr apps on the same machine. By default, Dapr uses 3500, so we use 3501 to avoid conflicts with our client's sidecar later. Path to your server.exe. This is the command to actually launch your server application. This separates Dapr's arguments from your application's arguments. You will see output from Dapr indicating it's starting, binding to ports, and then messages from your server application itself. Start the client application with Dapr. Open another new terminal for the client and run Dapr Run appid client appid path to your client.exe. Appid client appid, a unique ID for the client application. Path to your client.exe launches your client application. The client application's Dapr sidecar will default to listening on port 3500. Observing the interaction. Once both applications are running, your client app will execute its Dapr service invocation call to http localhost :3500/v 1.0/invoke/server-app-id/method/greetings. The client app's Dapr sidecar receives this request. It uses its internal service discovery, handled by the Dapr control plane, to find the actual network address of the server app-id's Dapr sidecar. It then routes the request securely and reliably to the server app's Dapr sidecar. The server app's Dapr sidecar receives the request, identifies that it's for the greetings method, and forwards it to port 5000 of its server app. The server app responds with "Hello" from Dapr-enabled server. This response travels back through the server app's Dapr sidecar, then to the client app's Dapr sidecar, and finally to the client app. You will see output in the client's terminal showing the successful invocation and the response received. 3.4 Understanding Dapr's log output. When you run an application with Dapr, both your application's output and the Dapr sidecar's output appear in the same terminal. It's important to distinguish between them to understand what's happening. Dapr sidecar logs typically start with info, or warn, and include details about its internal operations, such as port bindings, e.g., time equals 2023 to 1 to 0 1 T1200.000Z, level equals info MSG equals gRPC server listening on 50,001. Loaded components, e.g., time equals 2023 to 1 to 0 1 T1200.000Z, level equals info MSG equals component loaded. Name, state store type, stateReady/v1. Service invocation attempts, e.g., time equals 2023 to 1 to 0 1 T12 00.000Z level equals info MSG equals calling appid. Server appid verb get path greetings. Monitoring these logs is crucial for debugging. If a call fails, Dapr's logs will often provide detailed information about why, such as network issues, unroutable service IDs, or misconfigured components. 3.5 Interacting with Dapr directly optional. For deeper understanding, you don't always need a full application to interact with Dapr. You can use command line tools like curl to directly call Dapr's HTTP API, demonstrating its res-tful nature. Assuming your server app is running with Dapr, as in step 3.3.1, you can test service invocation by manually calling the server appid through a separate Dapr sidecar, or by mimicking how your client's sidecar would communicate. A simpler demonstration is to interact directly with Dapr's State Management API, which doesn't require a second Dapr-enabled application. Let's try. Ensure Dapr is initialized. Dapr status should show OK. Start a simple long-running Dapr sidecar. Dapr run appid mytestapp Dapr HTTP port 3500 port 3000 echo. Dapr sidecar running for manual testing. The echo command is just a placeholder to keep the terminal open with the Dapr sidecar running. Open a new terminal and use curl to save a state. Curl x post h content type application/json d key my-key value my-value http localhost :3500/v 1.0/state/statestore. This tells Dapr's sidecar, on port 3500, to save a key value pair my-key my-value to the default statestore component, which is redis, configured by Dapr init. Retrieve that state. Curl http localhost :3500/v 1.0/state/statestore/my-key. You should see my-value returned. This demonstrates that Dapr exposes a consistent, programmatic API that any client can interact with, fundamentally decoupling your application logic from the underlying infrastructure. 3.6 Cleaning up your local environment. When you're done experimenting, it's good practice to clean up the Dapr runtime and its associated containers. Stop Dapr-enabled applications. You can simply press Ctrl+C in each terminal where you ran Dapr run. This will gracefully shut down both your application and its associated Dapr sidecar. Uninstall Dapr's local components. Dapr uninstall all. This command stops and removes the redis and zipkin Docker containers, and deletes the Dapr runtime binaries and component configuration files from your local machine, effectively resetting your Dapr environment. 3.7 Chapter Summary and Next Steps. Congratulations! You've successfully installed Dapr, initialized it in self-hosted mode, and run your first Dapr-enabled distributed application using the Dapr run command. You've seen how Dapr abstracts away network communication and service discovery, allowing your client application to invoke another service without knowing its actual address. You've also had a glimpse into how to observe Dapr's logs and even interact with its API directly. This foundational practical experience sets the stage for a deeper dive into Dapr's powerful building blocks. In the upcoming chapters, we will explore each of them in detail, starting with the ubiquitous challenge of service-to-service communication. 4. Service-to-service communication. Invoking distributed services. In a microservices architecture, services rarely exist in isolation. They frequently need to communicate with each other to fulfill business processes. This inter-service communication is one of the most fundamental and frequent operations in a distributed system, yet it's fraught with challenges. How do services find each other? How do they communicate securely? What happens if a service is temporarily unavailable? How do you ensure the communication is resilient? Before Dapr, developers would often implement complex service discovery mechanisms, use client-side load balancing, manually add retry logic, implement circuit breakers, and configure mutual TLS for secure communication within their applications. This led to significant boilerplate code and inconsistent resilience patterns across different microservices. Dapr's service invocation building block simplifies this entire process, externalizing these complexities into the Dapr sidecar. Your application merely declares its intent to invoke another service, and Dapr takes care of the intricate details. 4.1 The challenge of service invocation in distributed systems. Let's quickly recap the pain points. Service discovery. How does Service A know the network address, IP, and port of Service B? This is dynamic in modern environments like Kubernetes, where service instances come and go. Resilience. Networks are unreliable. What if Service B is temporarily down, slow, or returns an error? Service A needs retry mechanisms with exponential backoff, timeouts, and circuit breakers to prevent cascading failures. Security. Communication between services should be authenticated and encrypted. This typically involves managing certificates and implementing mutual TLS, MTLS. Observability. How do you trace a request as it hops between multiple services to understand its overall path and latency? Load balancing. If multiple instances of Service B are running, how does Service A distribute requests among them? Protocol diversity. While most services use HTTP or gRPC, some might use different protocols or require specific message formats. Without Dapr, addressing these issues for every single service invocation point requires significant engineering effort and can quickly clutter your business logic with infrastructure concerns. 4.2 How Dapr simplifies service invocation. The sidecar proxy. Dapr introduces a consistent, platform-agnostic way for applications to invoke methods on other Dapr-enabled applications. It does this by leveraging the sidecar pattern we discussed in Chapter 2. When an application wants to invoke a method on another service, it makes a simple call to its local Dapr sidecar. The Dapr sidecar then acts as a proxy. Application initiates call. Your application makes an HTTP or gRPC request to its Dapr sidecar, specifying the target application ID and the method to invoke. This communication is always over localhost. Dapr sidecar intercepts. The calling application's Dapr sidecar receives the request. Discovery and resolution. The Dapr sidecar uses its internal service discovery capabilities, often leveraging the underlying platform like Kubernetes DNS or Dapr's placement service for actors to find the network location of the target application's Dapr sidecar. Resilience policies applied. Before sending the request, the Dapr sidecar applies configured resilience policies, such as retries or circuit breakers. Secure communication. The Dapr sidecars communicate securely using MTLS, which is automatically enabled in most Dapr deployments via the Dapr Sentry service. Load balancing. If multiple instances of the target service are available, Dapr's sidecar will load balance requests among them. Target service invoked. The receiving Dapr sidecar forwards the request to the specified application method on the target service, which is listening on its app port. Response returned. The response travels back through the Dapr sidecars to the calling application. This entire process is transparent to your application. Your code remains clean, focusing only on what service to call and which method, without needing to know how to find it, how to secure it, or how to make the call resilient. 4.3 Invoking services with Dapr. The API. The Dapr Service Invocation API is straightforward. It's accessible via both HTTP and gRPC. Most Dapr SDKs, for popular languages like Go, Python, Java, Net, abstract these raw API calls into more idiomatic library methods, but understanding the underlying API is key. HTTP API example. To invoke a method named processOrder on a service with the Dapr Application ID ordering service, your application would make an HTTP post request to post HTTP localhost, Dapr port /v 1.0 invoke app id method name, where Dapr port is the HTTP port your Dapr sidecar is listening on default 3500. Appid is the Dapr application ID of the target service, e.g., ordering service. Method name is the name of the method to invoke on the target service, e.g., process order. The request body and headers would be passed through by Dapr to the target service. For example, to send a JSON payload. In your application code, conceptually, make an HTTP post call to HTTP localhost :3500/v 1.0/invoke/ordering service/method/process order. Add contents type. Application/JSON header. Add JSON body. Ordered. 123 items. Item A, Item B. If your ordering service is designed to receive HTTP post requests on its process order endpoint, it will receive the request exactly as if the client had called it directly, but with all the Dapr benefits applied implicitly. You can also use HTTP GET, PUT, delete, or even arbitrary HTTP verbs with this API. gRPC API example. For applications using gRPC, Dapr offers a similar gRPC API. Instead of constructing an HTTP URL, you'd use a Dapr gRPC client to call the invoke service method. This is often preferred for performance-sensitive scenarios due to gRPC's efficient binary serialization and long-lived connections. Dapr SDKs provide high-level wrappers for this. Your application code would then make an RPC call like client.invokeService, ordering service, process order, request data, where client refers to the Dapr gRPC client. 4.4 Configuring resilience for service invocation. One of the most valuable aspects of Dapr service invocation is its ability to apply resilience policies transparently. Dapr does not implement the resilience logic directly in your application code. Instead, it enables you to define policies declaratively through resilience configuration. You define resilience policies in a YAML file, which Dapr then applies to all calls made through its sidecars. This configuration can include rules for timeouts, how long Dapr should wait for a response before considering the call a failure, retries, how many times Dapr should retry a failed call, often with exponential backoff and jitter to avoid overwhelming the target service. Circuit breakers, a pattern to automatically stop calls to a failing service for a period after a certain number of failures, preventing cascading failures and giving the failing service time to recover. Once the circuit opens, Dapr can periodically check its health before closing the circuit again and resuming calls. For example, a resilience policy might look something like this in a YAML file. API version, dapr.io/v1 alpha 1. Kind, resiliency. Metadata, name, my resilience policy. Spec, policies, retries, default, policy, constant. Duration, 5s. Max retries, 3. Timeouts, default, 5s. Circuit breakers, default. Max requests, 1. Interval, 10s. Timeout, 60s. Rolling window, 60s. Targets, apps, my target service, retry, default. Timeout, default. Circuit breaker, default. This conceptual configuration tells Dapr to apply a default retry policy, 3 retries with 5-second duration, a 5-second timeout, and a specific circuit breaker configuration to calls targeting my target service. When you deploy this resiliency component manifest, Dapr sidecars will automatically pick it up and apply these behaviors to invocations without recompiling your application. This declarative approach centralizes your resilience logic, ensures consistency across your services, and keeps your application code focused on business logic. 4.5 Service-to-service communication with different protocols. While HTTP and gRPC are primary, Dapr can facilitate communication between services that use different underlying protocols on the network, as long as Dapr handles the method invocation. For example, your service A, written in Python, could make an HTTP call to its Dapr sidecar to invoke service B, written in Java. Service B might then expose its internal method via a Dapr-compatible HTTP endpoint. The beauty here is that the language differences are handled by Dapr. The Dapr sidecar acts as a universal communication layer between your applications, converting between protocols if needed or simply acting as a router. This flexibility extends to handling requests from non-Dapr-enabled applications as well. You can configure Dapr to expose your Dapr-enabled service to external clients or other plain microservices via an ingress component. Dapr then handles the secure and resilient routing of these external requests to your Dapr-enabled inner service. 4.6 Case Study: Streamlining an e-commerce order flow. Consider an e-commerce platform. When a customer places an order, several microservices need to communicate. Shopping cart service receives the order request. It needs to call inventory service to reserve stock. It then calls payment service to process the payment. Finally, it calls order fulfillment service to initiate shipping. Without Dapr, each shopping cart service developer would need to set up its own client for inventory service, payment service, and order fulfillment service. This would involve knowing their URIs, e.g., http inventory-service.production-cluster-local 8080, configuring client-side retry policies for each call, possibly setting up MTLS certificates, adding circuit breaker logic. This is repetitive, error-prone, and leads to inconsistencies. With Dapr, the shopping cart service simply makes 3 calls to its local Dapr sidecar. Dapr service.invoke, inventory service, reserve stock, order details. Dapr service.invoke, payment service, process payment, order details. Dapr service.invoke, order fulfillment service, initiate shipping, order details. Dapr then handles all the underlying complexities. Service discovery, MTLS between sidecars, retries if inventory service is momentarily busy, and circuit breaking if payment service is having issues. The developers focusing on shopping cart service can entirely concentrate on the business logic of order processing, leading to faster development and more robust applications. 4.7 Chapter Summary and What's Next. The service invocation building block is the cornerstone of effective inter-service communication in a Dapr-enabled microservices architecture. By abstracting away the complexities of service discovery, resilience, security, and load balancing, Dapr allows developers to focus on the unique business logic of their applications. The consistent API, coupled with declarative resilience configuration, ensures your distributed calls are robust and maintainable. In the next chapter, we will shift our focus from transient communication to persistent data. We will explore Dapr's state management building block, which provides a unified way to store and retrieve data across various backing stores, further simplifying distributed application development. 5. Managing state. Storing and retrieving data reliably. In any application, managing data is fundamental. In the context of distributed systems, where multiple services often need to access, share, or persist information, state management becomes a significantly challenging endeavor. Should each microservice have its own database? How do you ensure consistency across services? What if you need to use different types of databases for different purposes? Migrating from one database technology to another can be a monumental task when direct database drivers are embedded deep within application code. Dapr's state management building block addresses these complexities by providing a unified, consistent API for storing and retrieving key-value pairs, regardless of the underlying state store technology. This abstraction liberates your application code from specific database SDKs and connection concerns, making your services more portable and adaptable. 5.1 The challenge of state in distributed systems. In monolithic applications, state management is often centralized. A single database serves all components. In a microservices architecture, the prevailing pattern is database per service, meaning each service owns its data. While this promotes independence and loose coupling, it introduces new problems: technology diversity and headache. One service might use a relational database, another a NoSQL document database, and yet another a key-value store. Developers need to learn and integrate different SDKs, connection patterns, and data models for each. Consistency across services. Ensuring eventual consistency or orchestrating distributed transactions across different services and their disparate databases is notoriously difficult. Operational burden. Managing and monitoring multiple types of data stores adds significant operational overhead. Portability. If your application is tightly coupled to a specific cloud provider's database service or a proprietary database, migrating to a different environment becomes a costly rewrite. Caching and concurrency. Implementing caching at the application level and handling concurrent updates to shared data without race conditions requires careful design. The Dapr State Management building block aims to solve these problems by providing a standardized interface that abstracts away the specific implementation details of the underlying state stores. 5.2 How Dapr simplifies state management. the pluggable component approach. Dapr's approach to state management is built on its robust component model. Your application interacts with Dapr to perform state operations, and Dapr, in turn, interacts with the configured state store component. Here's how it works. Application intent. Your application decides it needs to save a piece of data, a key-value pair, or retrieve it. Call to Dapr sidecar. The application makes a simple, standard HTTP or gRPC call to its local Dapr sidecar, specifying the key, the value, and optionally, which state store component to use. Dapr intercepts. The Dapr sidecar receives the request. Component selection. If not explicitly named, Dapr uses the default state store. Dapr then uses the configured state store component to handle the actual data persistence. Data persistence. The Dapr sidecar translates the generic state request into the specific commands, protocols, and APIs understood by the chosen state store, e.g., Redis commands, Cosmos DB SDK calls, PostgreSQL queries. Response. The result of the operation, success, failure, or the retrieved value, is returned back through the Dapr sidecar to your application. The key benefit here is that your application doesn't need to know anything about Redis, Cosmos DB, or any other specific database. It simply relies on Dapr's consistent API for state management. This means you can swap out the underlying state store by simply changing a Dapr component configuration without modifying or recompiling your application code. 5.3 Storing and Retrieving State. The API. Dapr's state management API is simple and focuses on atomic key-value operations. HTTP API example. To save a state, e.g., a customer's order preference, represented as a JSON object. With a key customer 123 to a state store named MyStateStore, your application would make an HTTP post request to post HTTP localhost, Dapr port/v 1.0 state store name, with a JSON body containing the key-value pair. The Dapr sidecar's default HTTP port is 3500. Key, customer 123. Value, preferred language, NUS. Receive marketing emails, true. Options, concurrency, last write wins. Consistency, strong. Store name, the name of the configured state component, e.g. MyStateStore. If omitted, Dapr uses the default. Key, the unique identifier for your state. Value, the data you want to store. This can be any serializable data, JSON, plain text, binary. Options, optional parameters for concurrency control, e.g., last write wins or EDAG for optimistic concurrency, and consistency, e.g., strong or eventual. Not all state stores support all options. To retrieve this state, you would make an HTTP GET request. Get HTTP localhost, Dapr port/v 1.0 state store name key. Example, HTTP localhost :3500/v 1.0/state/my-state-store/customer-123. The response would be the JSON value stored under customer 123. To delete a state, delete HTTP localhost, Dapr port/v 1.0 state store name key. gRPC API example. Similar to service invocation, Dapr provides a gRPC API for state management. Dapr SDKs typically offer save state, get state, and delete state methods that map directly to these gRPC calls, providing a more natural programming experience in your chosen language. This is generally preferred for performance over the HTTP API. 5.4 State Store Components, enabling diverse storage options. The real power of Dapr's state management relies on its extensive collection of state store components. These are pre-built integrations that allow Dapr to connect to various databases and storage solutions. A state store component is configured via a YAML file, much like the general Dapr components we discussed. This file specifies the type of state store and its connection details. API version, dapr.io/v1alpha1. Kind, component. Metadata, name. MyStateStore hash. This is the store name used in the API call above. Spec, type. StateRedis hash specifies Redis as the state store. Version, v1. Metadata, name, Redis host. Value, localhost :6379, hash connection string for RIDIs. Name, RIDI's password. Secret keyref. Name, RIDI's password hash reference a secret for the password. Key, password. In this example, name. My state store is the friendly name you'll use in your application's Dapr State API calls. Type. StateRIDIs tells Dapr to use the RIDI's state store component. Dapr supports many others, like state.azure.cosmosdb, state PostgreSQL, state SQL Server, state.couchbase, and so on. Metadata. This section contains store-specific configuration, like the RIDI's host and port. Secret keyref demonstrates how Dapr can retrieve sensitive information like passwords from a secret store, often configured via the secret management building block, which we'll cover later. Dapr's component model allows you to deploy the same application code developed with StateRIDIs locally, and then deploy it to a production environment with state.azure.cosmosdb simply by changing the component YAML without touching your application layer. 5.5 Concurrency and Consistency. Distributed state management introduces complexities around concurrent updates and data consistency. Dapr provides mechanisms to address these. Concurrency options. Last write wins default. If multiple clients try to update the same key, the last update received by Dapr is the one that persists. This is suitable for non-critical data or when eventual consistency is acceptable. Optimistic concurrency control (ETAGs). For critical data, Dapr supports ETAGs, entity tags. When you retrieve state, Dapr returns an ETAG for that version of the data. When you save an update, you provide this ETAG. If the ETAG matches the current version in the store, the update proceeds. If it doesn't, meaning someone else modified the data in between, Dapr rejects the update, preventing lost updates. Your application can then decide to refetch and reapply changes. Consistency options. Strong consistency guarantees that a read operation will always return the most recently written value. This might come at the cost of higher latency. Eventual consistency. A read operation might return an older value temporarily, but eventually, all replicas will converge to the most recent value. This offers better performance and availability. Not all state store components support all consistency or concurrency options. Dapr abstracts these options where possible, but it's important to understand the capabilities of your chosen underlying state store. 5.6 Transactional State Management. For operations that involve multiple state updates that must either all succeed or all fail together, an all-or-nothing operation. Dapr supports transactional state management. This means you can group several save and delete operations into a single transaction. If any part of the transaction fails, the entire transaction is rolled back, ensuring data integrity. To perform a transaction, you'd use Dapr's transactional API, which again is available through HTTP or gRPC. You'd specify the operations, save and delete, along with their keys and values, and Dapr would ensure the transaction is committed atomically by the backing state store if it supports transactions. Example, conceptual HTTP, post to v1.0 state store name transaction. Operations. Operation, upsert. Request, key. User profile 123. Value, name, Alice email, alice@example.com. Operation, delete. Request, key, temporary item 456. This single call would instruct Dapr to perform both the upsert and delete as part of one transaction against the store name state store. 5.7 Case Study. User Session Management. Consider an e-commerce application where user session data, e.g., items in a shopping cart, last viewed products, login status, needs to be stored. This data is critical for a good user experience, but can vary greatly in volume and access patterns. Problem: if you directly integrate your user service with RIDIs, a popular choice for sessions, you'd need the RIDIs client library in your code, manage connection pools, handle serialization, and deal with retries. If you later decide to migrate to Azure Cache for RIDIs or a different specialized session store, you'd have to rewrite significant portions of your user service. Dapr solution. With Dapr, the user service simply calls Dapr service save state, my session store, user id123, session data, and Dapr service get state, my session store, user id123. The my session store Dapr component can be configured for local development using stateReadies pointed at a locally running Redis instance. For production, the same my session store component can be configured to use stateReadies pointed at a managed Azure cache for Redis, or even state.cosmosdb if you want a globally distributed session store with strong consistency features. Your user service code remains unchanged, providing maximum flexibility and portability. 5.8 Chapter Summary and What's Next. The Dapr State Management Building Block is a powerful tool for abstracting the complexities of data persistence in distributed applications. By offering a standardized API for key-value operations and a pluggable component model, it allows developers to easily store and retrieve data across a wide array of backing stores without coupling their application code to specific database technologies. This significantly enhances application portability, simplifies development, and centralizes state management concerns. In the next chapter, we'll shift our focus from direct key-value state persistence to event-driven communication. We will explore Dapr's publish-subscribe building block, a crucial element for building loosely coupled, asynchronous microservices architectures. 6. Event-driven architectures. Publish-subscribe for asynchronicity. In a distributed system, not all communication needs to be a direct, synchronous request-response interaction like the service invocation we discussed in Chapter 4. Often, services need to react to events occurring in other parts of the system without needing to know the exact identity or location of the sender. This loosely coupled, asynchronous communication pattern is where publish-subscribe, pub-sub shines, forming the backbone of event-driven architectures. Implementing pub-sub reliably in a distributed environment comes with its own set of challenges, from choosing and configuring message brokers to handling message delivery guarantees and ensuring consistency across different messaging systems. Dapr's publish-subscribe building block simplifies this by offering a standardized, resilient API for sending and receiving messages, abstracting away the specifics of the underlying message broker. 6.1 The challenge of asynchronous communication and pub-sub. Synchronous requests, while straightforward for immediate interactions, can introduce tight coupling, reduce resilience, and hinder scalability. If a service needs to process a request that has long-running side effects, waiting synchronously for all operations to complete can lead to timeouts and poor user experience. Asynchronous communication via pub-sub helps decouple services, making the system more resilient and scalable. However, implementing pub-sub systems directly presents several challenges. Broker selection and integration. Every message broker, e.g., Kafka, RabbitMQ, Azure Service Bus, AWS SNS SQS, has its own SDK, configuration, and API. Developers need to learn and integrate these specific client libraries into their applications. Message delivery guarantees, ensuring messages are delivered at least once. At most once, or exactly once, requires careful handling of acknowledgements, retries, and deduplication logic within the application or via the broker. Topic management. Deciding on topic naming conventions, partitioning strategies, and consumer groups can get complex. Error handling and dead lettering. What happens to messages that cannot be processed? Proper mechanisms for dead letter queues and error recovery are essential. Portability. Migrating from one message broker to another, or even a different version of the same broker, often requires significant application code changes. Security and authorization. Securing access to topics and ensuring only authorized services can publish or subscribe. Dapr's pub-sub building block consolidates these complexities, providing a unified API for interacting with various message brokers. 6.2 How Dapr simplifies pub-sub. The Dapr Runtime as Message Gateway. Similar to state management and service invocation, Dapr acts as a transparent intermediary for pub-sub operations. Services publish messages to their Dapr sidecar, and Dapr handles forwarding them to the configured message broker. Similarly, consumer services register interest in specific topics with their Dapr sidecar, and Dapr pulls messages from the broker and delivers them to the application. Here's the flow: publishing a message. Your application wants to publish a message. It makes a simple HTTP or gRPC call to its local Dapr sidecar, specifying the message content and the pub/sub name, the Dapr component name for the message broker, and topic to which the message should be sent. The Dapr sidecar receives the message and publishes it to the configured message broker using the broker's specific client library and protocol. Subscribing to messages. Your application registers interest in a topic with its Dapr sidecar. This can be done programmatically or declaratively using a Dapr subscription component. Dapr continuously monitors the specified topic on the message broker. When a new message arrives, Dapr retrieves it from the broker, performs any necessary deserialization, and delivers it to a predefined HTTP endpoint on your application or via gRPC. Your application processes the message and then indicates success or failure to Dapr by returning a specific HTTP status code or a Dapr response. Dapr then handles the message acknowledgement or requeuing with the message broker. This pattern means your application is completely abstracted from the message broker's specific API. You write simple pub/sub logic and let Dapr manage the complex interaction with Kafka, RabbitMQ, or any other broker. 6.3 Publishing and subscribing. The Dapr pub/sub API. Dapr provides straightforward APIs for both publishing and subscribing. Publishing, HTTP API example. To publish a message to a topic named orders using a pub/sub component named myMessageBroker, your application would make an HTTP post request to post HTTP localhost, Dapr port/v 1.0/publish/pub/sub name/topic, with a JSON body containing the message payload. Example: post HTTP localhost :30 500/v 1.0/publish/my-message-broker/orders. Body: ordered XYZ789. Status: processed. Total amount: 99.99. The message content, ordered, status, total amount, is passed directly to the myMessageBroker component to be published to the orders topic. Subscribing, HTTP API example. When subscribing to messages, Dapr delivers messages from the message broker to a specific HTTP endpoint on your application. Your application generally needs to implement two things: a Dapr subscription endpoint. Dapr queries your application, by default, get Dapr/subscribe, to discover which topics it wants to subscribe to. Your application responds with a list of subscriptions. Example response from get Dapr/subscribe. Pub/sub name, myMessageBroker. Topic, orders. Root, orders processor. Pub/sub name, myMessageBroker. Topic, products. Root, products processor. This indicates that the application wants to subscribe to orders and products topics from myMessageBroker, and messages for orders should be sent to its orders processor endpoint, while messages for products go to products processor. Topic-specific endpoints. Your application implements the orders processor and products processor endpoints as HTTP post handlers to receive and process messages. When Dapr delivers a message, it will be the JSON body of the post request. Example payload from Dapr to your orders processor endpoint. id E67 BA053 to 667 to 46 38 to 89 29 E1 I67 I4 B4B. Dapr's message ID. Source: order service, Dapr app ID of publisher. Type: Dapr event cloud events type. Spec version 1.0. Data content type: application/JSON. Data: your actual message payload. Ordered XYZ789. Status: processed. Total amount: 99.99. Pub/sub name: myMessageBroker. Topic: orders. To acknowledge successful processing, your application should return a 200 OK HTTP status code. To signal a transient error and request redelivery, return 500 internal server error. Declarative subscriptions with components. For Kubernetes, Dapr also supports declarative subscriptions using YAML files, which is often preferred for managing subscriptions outside application code. API version. Dapr.io/v1 alpha 1. Kind, subscription. Metadata, name, order subscription. Spec, pub subname, my message broker. Topic, orders. Routes, default. Orders processor hash the endpoint on your subscriber app. Scopes. Order processor app, hash only allow this Dapr app to receive messages for this subscription. When this subscription component is deployed, Dapr automatically configures publishing and delivery for the specified order processor app. This means your application doesn't even need to implement the /Dapr/subscribe endpoint. 6.4 Pub Sub components, integrating with message brokers. Similar to state stores, Dapr integrates with various message brokers through Pub Sub components. These components abstract the specific API and configuration details for each broker. A Pub Sub component is configured in a YAML file specifying the type of broker and its connection parameters. API version. Dapr.io/v1 alpha 1. Kind, component. Metadata, name. My message broker hash the PubSub name used in the API call above. Spec, type. PubSub RabbitMQ specifies RabbitMQ. Version, v1. Metadata, name, host. Value, amp//localhost:5672 hash connection string for RabbitMQ. Name, durable. Value, true hash message durability setting. This component defines a My Message Broker PubSub component that uses RabbitMQ. You could easily switch this to PubSub Kafka, PubSub Azure Service Bus, or PubSub SNS SQS for AWS SNS SQS by changing the type and appropriate metadata without changing your application code. This provides robust portability across different messaging infrastructures. 6.5 Message delivery guarantees and error handling. Dapr works with the underlying message broker to provide reliable message delivery, usually offering at least once delivery semantics. This means a message might be delivered more than once in case of network issues or consumer failures. Your application should be designed to be idempotent, meaning processing the same message multiple times has the same effect as processing it once. For error handling, when your application returns a non-200 HTTP status code, e.g., 500 internal server error, Dapr will typically redeliver. Try to redeliver the message based on the broker's configuration and Dapr's retry policies. Dead letter queue, DLQ. If redelivery attempts are exhausted, Dapr can be configured to send the message to a dead letter queue on the broker for manual inspection and reprocessing. This is crucial for preventing message loss due to persistent application errors. 6.6 Cloud Event Standard. Dapr internally uses the Cloud Event specification for structuring messages passed between Dapr and your application. Cloud Events is a standardized format for describing event data in a portable way. When Dapr delivers messages from a PubSub component to your application, they are encapsulated in a Cloud Event. This consistency makes it easier for your applications to process events from various sources and promotes interoperability. You saw an example of this Cloud Event structure in the subscriber payload above. 6.7 Case Study. An e-commerce order management system. Revisiting our e-commerce platform, PubSub is essential for handling asynchronous workflows. Order placed. When the order service successfully processes an order, instead of directly calling other services, it publishes an order-placed event to the order's topic. Order service published to Dapr to RabbitMQ orders topic. Inventory update. The inventory service subscribes to the order's topic. When an order-placed event arrives, it updates stock levels. RabbitMQ orders topic, Dapr to inventory services order update endpoint. Shipping notification. The shipping service also subscribes to the order's topic. Upon receiving an order-placed event, it initiates the shipping process. RabbitMQ orders topic, Dapr to shipping services ship order endpoint. Customer notification. A separate notification service subscribes to events like order placed, order shipped, or payment failed to send relevant emails or SMS updates to the customer. RabbitMQ orders topic, Dapr to notification services send order confirmation endpoint. This loosely coupled design offers immense benefits. Scalability. Each service can scale independently based on its message processing load. Resilience. If the inventory service goes down, the order service can still publish order-placed events. When inventory service comes back online, it can process the backlog of messages. Extensibility, adding new services, e.g., a loyalty program service, that react to existing events like order placed, is simple. They just need to subscribe to the relevant topic without any changes to the order service. Reduced development overhead. Developers focus on the business logic of responding to events, not on integrating with a specific message broker. 6.8 Chapter Summary and What's Next. Dapr's Publish-Subscribe building block simplifies the development of event-driven architectures by providing a consistent, abstract API over various message brokers. This enables loosely coupled, resilient, and scalable microservices. By externalizing the complexities of message broker integration, ensuring reliable delivery, and leveraging standards like cloud events, Dapr significantly accelerates development and enhances architectural flexibility. With resilient service communication and reliable state management covered, the next logical step is to explore how Dapr helps applications interact with an even broader array of external systems, both for input and output, using its powerful bindings and triggers building block. 7. External systems integration, bindings and triggers. In the journey of building robust distributed applications, we've seen how Dapr simplifies service-to-service communication and state management. However, many applications don't operate in a vacuum. They need to interact with a multitude of external systems that aren't necessarily other Dapr-enabled microservices or standard data stores. This could include event sources like IoT devices, external APIs, legacy databases, file storage systems, cloud services, and more. Integrating with such diverse external systems often involves writing custom code for client SDKs, handling authentication, managing connection lifecycles, and grappling with unique protocols. This is where Dapr's bindings and triggers building block provides a powerful abstraction, allowing your application to interact with a vast array of external resources using standardized HTTP or gRPC APIs, simplifying integration and boosting portability. 7.1 The challenge of external system integration. The landscape of external systems is incredibly diverse. Integrating them into your microservices can be complex due to protocol diversity. Some systems communicate via HTTP, others via Kafka, AMQP, gRPC, or even proprietary protocols. Authentication and authorization. Each system might have its own method for securing access, API keys, OAuth, SAS tokens, etc. Data formats. Data might arrive as JSON, XML, Avro, protobuf, or custom binary formats. Error handling and retries. Handling transient failures, network latency, and idempotent operations for each external service requires specific error handling and retry logic. Versioning and SDK management. Keeping up with different SDK versions and API changes for numerous external services can be a maintenance nightmare. Portability. Tightly coupling your application to a specific cloud provider's proprietary services can make migration to another cloud or on-premises environment extremely difficult. Dapr's bindings and triggers building block tackles these challenges by providing a generalized way to interact with external resources, fostering loose coupling and flexibility. 7.2 Understanding Dapr bindings. Input and output. The bindings building block is effectively divided into two main categories. Input bindings, triggers. These allow Dapr to listen for events from an external system and then invoke a method on your application. Your application doesn't need to poll or maintain long-lived connections to the external system. Dapr handles that. When an event occurs, e.g., a new message in a queue, a file uploaded to blob storage, a new row added to a database, Dapr triggers your application's specified endpoint. Output bindings. These allow your application to invoke an operation on an external system. Instead of directly calling the external service's API, your application sends a simple request to its Dapr sidecar, and Dapr translates this into the appropriate call to the external system. This enables a true connect-to-anything approach where your application speaks a Dapr language, and Dapr translates it to the language of the external system. 7.3 Input bindings. Triggering your application. Input bindings define how Dapr connects to an external event source and pushes events to specific endpoints on your Dapr-enabled application. How it works. Define an input binding component. You create a Dapr component, YAML file, that specifies the type of external system and its connection details, e.g., an Azure storage queue, a Kafka topic, an MQTT broker. Configure application endpoint. Your Dapr-enabled application must expose an HTTP endpoint, e.g., new message, that Dapr will call when an event arrives from the bound external system. Automatic event delivery. Dapr listens to the external system. When an event occurs, it transforms it into a cloud event, similar to pub/sub messages, and makes an HTTP post request to your application's configured endpoint. Example input binding component Azure Storage Queue as a trigger. API version, dapr.io/v1alpha1. Kind component, metadata, name, storage queue binding hash name of the binding component. Spec type, bindings Azure Storage Queues hash type for Azure Storage Queues. Version, v1. Metadata, name, queue name. Value, myqueue hash name of the queue to listen to. Name, connection string. Secret keyref, hash retrieve connection, string from a secret store. Name, storage secrets. Key, storage connection string. Application endpoint, conceptual. Your Dapr-enabled application would simply have an HTTP post endpoint, for example, /myqueue_new_message, ready to receive messages. Post/myqueue_new_message. Body, id, source, type, data, / your actual message payload from the queue. Dapr handles polling the queue, receiving messages, and reliably delivering them to your application's endpoint. Your application processes the message and returns a 200 OK for success or other status codes for Dapr to manage retries or dead lettering. 7.4 Output bindings. Invoking external systems. Output bindings define how your application can send data or invoke operations on an external system. How it works. Define an output binding component. You create a Dapr component, YAML file, that describes the external system you want to interact with, e.g., an AWS S3 bucket, a Twilio account, a Kafka topic, a PostgreSQL database. Application invocation. Your application makes a simple HTTP post request to its local Dapr sidecar. The request specifies the name of the binding component, the operation to perform, e.g., create, delete, send, and the data to send. Dapr interacts with external system. The Dapr sidecar receives the request, translates it into the appropriate API call for the external system using its specific SDK, performs the operation, and returns the result to your application. Example output binding component, Twilio for sending SMS. API version, dapr.io/v1alpha1. Kind component, metadata, name, Twilio binding hash name of the binding component. Spec type, bindings Twilio hash type for Twilio SMS. Version, v1. Metadata, name, account SID. Secret keyref, name, Twilio secrets. Key, account SID. Name, auth token. Secret keyref, name, Twilio secrets. Key, auth token. Name, from. Value, +155512345567, hash your Twilio phone number. Application invocation, HTTP API example. Your application would make a post request to the Dapr sidecar to send an SMS. Post HTTP localhost, Dapr port /v1.0 bindings binding name, with a JSON body specifying the operation and data. Operation, send. Data, 2 +15559876543. Body, hello from Dapr. Binding name. The name of the binding component, Twilio binding in this case. Operation, the action to perform, e.g., send for Twilio, create for file storage, query for databases. This value depends on the binding type. Data, the payload to send to the external system. Dapr supports a vast and growing list of binding types, including protocols like HTTP, gRPC, MQTT, Apache Kafka, Azure Blob Storage, AWS S3, various databases, email services, and much more. This means your application code remains clean and generic, while Dapr handles the diverse integration logic. 7.5. Combining bindings and triggers for event-driven flows. The power of bindings is truly unlocked when you combine input and output activities, particularly in event-driven systems where a single external event can trigger multiple downstream actions. Consider an application that processes images. Input trigger. A Dapr input bindings Azure Blob Storage, listens for new image, uploads in an Azure Blob Storage container. When a new image is uploaded, Dapr triggers the image processor service's new image endpoint. Processing. The image processor service processes the image, e.g., resizing, applying a watermark. Output binding. After processing, the image processor service might use an output bindings Azure Blob Storage, to save the processed image to a different container, and another output bindings Azure Service Bus, to send a notification message to a service bus topic for downstream services. This modular approach allows you to build complex workflows by chaining together Dapr's capabilities, without writing repetitive integration code within your application. 7.6. Portability through binding components. The bindings and triggers building block is a prime example of Dapr's commitment to portability. If you develop an application that reads from a Kafka topic using bindings Kafka and writes to an S3 bucket using bindings Oz S3, you can later deploy the exact same application code to an Azure environment by simply changing the Dapr component YAML files to use bindings Azure Event Hubs and bindings Azure Blob Storage, respectively. The application code only interacts with the generic Dapr binding API, making it truly adaptable to different deployment environments. 7.7. Case study. An IoT data ingestion pipeline. Imagine an IoT solution where devices send telemetry data. Problem: devices might send data via MQTT. A traditional approach would require your ingestion service to include an MQTT client library, handle connection management, subscribe to topics, and parse incoming messages. Then, to store this data in a database, you'd need the database's specific SDK, write insertion logic, and manage error handling. If you later wanted to swap MQTT for Kafka, or move from PostgreSQL to Cosmos DB, significant code changes would be needed. Dapr solution. MQTT input binding. A Dapr input bindings MQTT, is configured to listen for incoming telemetry from the MQTT broker. This binding triggers the ingestion service's telemetry endpoint whenever a new message arrives. Telemetry processing. The ingestion service receives the telemetry data from Dapr, performs any necessary validation or lightweight processing. Database output binding. The ingestion service then uses a Dapr output bindings PostgreSQL, to persist this processed telemetry data to a PostgreSQL database. It simply sends a JSON payload to its Dapr sidecar with an operation: query and data, SQL, insert into telemetry. This approach ensures the ingestion service is clean and maintains focus on its core task: processing and persisting telemetry. It doesn't need to know anything about MQTT-specific clients or SQL drivers. Dapr handles all the details. This provides seamless integration and significant flexibility for future infrastructure changes. 7.8. Chapter summary and what's next. The Dapr bindings and triggers building block provides an invaluable solution for integrating your microservices with a vast ecosystem of external systems. By separating the concerns of external system interaction from your application logic, Dapr empowers you to build applications that are more flexible, maintainable, and portable. It simplifies how your services receive events from and send data to the world beyond your application boundaries, significantly reducing development effort. So far, we've focused on how Dapr helps your application communicate and manage data. But what about securing these communications and ensuring sensitive data is protected? That's the topic of our next chapter: secret management and access control. 8. Securing your applications. Secret management and access control. In the interconnected world of distributed systems, security is not an afterthought. It's a foundational requirement. Every microservice, by its very nature, communicates over a network, and often interacts with external resources that require authentication. Hard-coding credentials, relying on environment variables only, or manually rotating sensitive information are not viable strategies for production-grade applications. Poor security practices can lead to devastating data breaches and compromised systems. This is where Dapr's capabilities for secret management and access control become indispensable. Dapr helps you retrieve sensitive information securely and control which services can communicate with each other, minimizing the attack surface and enhancing compliance. 8.1. The challenge of security in distributed systems. Securing microservices introduces complexities far beyond those of monolithic applications. Credential management. Applications need access to database connection strings, API keys for external services, cloud access tokens, and cryptographic keys. How are these stored, distributed, and rotated securely without being exposed in source code or easily accessible configurations? Inter-service authentication. How do services reliably authenticate each other? When Service A calls Service B, how does Service B know that the request legitimately came from Service A and not a malicious actor? Authorization, access control. Beyond authentication, how do you specify which services are allowed to call certain methods on other services? Not all services should have full access to every endpoint. Auditing and compliance. Tracking who accessed what when and from where is crucial for security audits and regulatory compliance. Vulnerability surface. Each microservice, with its own dependencies and network endpoints, presents a potential vulnerability point, requiring robust security measures at every layer. Dapr addresses these challenges by externalizing secret access and providing a layer of access control that complements underlying platform security. 8.2. Secret management. Securely accessing sensitive information. Dapr's secret management building block provides a secure and unified way for your Dapr-enabled applications to retrieve secrets. This abstracts away the specifics of various secret stores, allowing you to use different providers without changing your application code. How it works. Define a secret store component. First, you define a Dapr secret store component as a YAML file. This component specifies the type of secret store, e.g., Azure Key Vault, AWS Secrets Manager, HashiCorp Vault, Kubernetes Secrets, and its necessary configuration details like credentials or URLs. Application requests secret. Your application simply asks its local Dapr sidecar for a secret by its name, optionally specifying which secret store to use. Dapr retrieves secret. The Dapr sidecar receives the request, connects to the configured secret store, retrieves the requested secret using the secret store's native API, and returns it to your application. Crucially, your application never directly interacts with the secret store's API. It only talks to its local Dapr sidecar over localhost. All sensitive information required to authenticate to the secret store itself, e.g., Azure Service Principal credentials, AWS IAM roles, is configured within the Dapr component and handled by the Dapr sidecar. HTTP API example. To retrieve a secret named DB connection string from a secret store component named MySecretStore, created in a Dapr component file, your application would make an HTTP GET request to get HTTP localhost, Dapr port /v 1.0 secret store name secret name. Example, HTTP localhost :3500/v 1.0/secrets/my-secret-store/db-connection-string. The response would be a JSON object containing the secret. DB connection string. Server equals my-db.example.com, database equals prod, user ID equals user, password equals mysecret. Secret store component example, Kubernetes secrets. API version, dapr.io/v1 alpha 1. Kind, component. Metadata, name, Kubernetes secrets hash the name for the secret store. Spec type. Secret store's Kubernetes hash integrates with Kubernetes secrets. Version, v1. Metadata, hash no specific configuration needed, uses Kubernetes' built-in service account. With this, your application simply asks Dapr for a secret called database secret from the Kubernetes secret store. and Dapr retrieves it from the Kubernetes cluster's secret facility. This decouples the application code from Kubernetes-specific authentication methods. This approach offers significant advantages. Centralized secret management. Leverages industry-standard secret management solutions, making it easier to rotate credentials, manage access, and audit usage. Reduced attack surface. Secrets are not hard-coded or exposed in environment variables visible to other processes on the same machine. Portability. The application code works identically whether it's retrieving secrets from Azure, Key Vault in the cloud, or HashiCorp Vault on-premises. 8.3 Access control, limiting who can call whom. Beyond simply retrieving secrets, Dapr also enables granular access control policies to restrict how services can communicate with each other. This is crucial for implementing a least privilege security model, where services only have the necessary permissions to perform their designated tasks. Dapr achieves this through access control lists, ACLS, which are defined declaratively using a Dapr configuration. While not a full-fledged network policy engine like those in Kubernetes, Dapr's ACLs provide an application-level layer of authorization for inter-service communication. How it works. Define a network access policy. You create a Dapr configuration component, YAML file, that specifies the access control rules. This configuration is often applied cluster-wide or to specific namespaces. Dapr enforces policies. When a Dapr sidecar receives an incoming service invocation request, it checks the configured. If the calling application, identified by its Dapr AppHid, does not have permission to invoke the target application's method, Dapr rejects the request before it even reaches your application, returning an unauthorized error. Access control configuration example. API version, dapr.io/v1alpha1. Kind, configuration. Metadata, name, access control policy. Spec access control, default action, deny hash default. Deny all requests unless explicitly allowed. Policy, AppHid, checkout service hash from this calling app. Default action. Allow all calls from checkout service by default. Hash defines specific restrictions for this app if needed. AppHid, payment service hash from this calling app. Default action. Deny all calls from payment service by default. Operations, name, process order hash except for this specific operation method. HTTP verb. Host, action, allow. AppHid, email service hash from this calling app. Default action. Deny all calls from email service by default. Operations, name, /API/v1/email, hash match specific path endpoint. HTTP verb. Host, action, allow. In this example, default action, deny provides a secure by default posture. Unless explicitly allowed, inter-service communication is blocked. Checkout service is allowed to call any method on any service. This is a common pattern for high-level orchestrator services, but should be used with caution. Payment service is only allowed to call the process order method on services it's trying to invoke. Email service is only allowed to call the /API/v1/email endpoint via post method. This policy applies the deny permission to all operations unless explicitly added to one of the allow permission lists. This provides fine-grained control over inter-service communication flows at the application layer, supplementing network policies that might operate at a lower layer, e.g., Kubernetes network policies. 8.4 Automatic MTLS for secure communication. A crucial security feature built directly into Dapr, especially when deployed in Kubernetes, is automatic mutual TLS, MTLS, for inter-Dapr communication. When Dapr init is run in Kubernetes, the Dapr control plane deploys a sentry service. The sentry service acts as a certificate authority, generating and distributing MTLS certificates to all Dapr-enabled applications. These certificates are used by the Dapr sidecars to establish secure, encrypted, and mutually authenticated connections between themselves. This means all traffic between Dapr-enabled microservices is encrypted in transit, and the identity of the calling service is cryptographically verified, all without any application configuration or code changes. This out-of-the-box MTLS significantly enhances security by preventing eavesdropping and ensuring only legitimate Dapr-enabled services can communicate. 8.5 Case Study. Protecting Payment Gateway Credentials. Consider a payment service that needs to interact with an external payment gateway. This interaction requires an API key and a merchant ID. Problem: storing these credentials directly in configuration files or environment variables is a security risk. They could be accidentally committed to source control or exposed to unauthorized users who gain access to the server. Dapr Solution: Secure Secret Store. First, the API key and merchant ID are stored in an enterprise-grade secret store like Azure Key Vault or HashiCorp Vault. Dapr Secret Store Component. A Dapr component is created that defines the connection to this secret store. Payment Service Access. In Dapr-enabled code, the payment service would then simply call Dapr Client Get Secret, MyKeyVault, Payment Gateway API Key, and Dapr Client Get Secret, MyKeyVault, Merchanted. Dapr handles retrieval. The payment service's Dapr sidecar would then securely connect to Azure Key Vault using its own managed identity or configured credentials, retrieve the secrets, and return them to the payment service. This ensures the payment gateway credentials are not directly exposed in the payment service code or its deployment configuration, minimizing the risk of compromise. Furthermore, if you need to rotate these credentials, you update them in the secret store, and Dapr automatically fetches the new values. Combined with Dapr's automatic MTLS, the communication between payment service and other Dapr-enabled services also stays secure. 8.6 Chapter Summary and What's Next. Security is non-negotiable in distributed systems, and Dapr provides powerful capabilities to address common security challenges. The Secret Management Building Block offers a consistent, secure way to access sensitive credentials from various secret stores, decoupling your application from specific secret management technologies. Dapr's declarative access control lists enable fine-grained authorization for inter-service communication, reinforcing the principle of least privilege. And built-in automatic MTLS ensures secure, encrypted, and authenticated communication between your Dapr-enabled microservices. With secrets and access control covered, we've laid a strong foundation for building secure and reliable applications. In the next chapter, we'll explore some more advanced Dapr patterns, including the actor model for stateful services, enhancing observability, and managing application configuration dynamically. 9. Advanced Patterns. Actors, Observability, and Configuration. So far, we've explored Dapr's foundational building blocks for communication, state management, eventing, integration, and security. These enable you to build robust, distributed applications. But Dapr's capabilities extend further, providing solutions for more specialized patterns, enhancing visibility into your systems, and simplifying dynamic configuration. This chapter delves into some of these advanced features: the actor model, comprehensive observability, and dynamic application configuration. 9.1 Actors. Building scalable, stateful microservices. Traditionally, microservices are designed to be stateless to simplify scaling and resilience. However, many real-world problems require stateful processing, such as managing a game session, tracking the state of an IoT device, or handling a long-running workflow. Building highly concurrent, fault-tolerant stateful services can be extremely complex, often leading to race conditions, synchronization issues, and difficulty reasoning about system behavior. The actor model provides a powerful paradigm for managing stateful concurrency. An actor is an isolated, independent unit of computation and state that communicates exclusively by sending and receiving asynchronous messages. Each actor processes messages one at a time, eliminating the need for locks and reducing complexity. Dapr includes a lightweight, distributed implementation of the virtual actor pattern. This combines the benefits of the actor model with Dapr's distributed system capabilities, simplifying the development of scalable and fault-tolerant stateful services. How Dapr actors work? Actor definition. You define your actor within your application code. This includes its methods, the messages it can receive, and its internal state. Dapr actors are identified by their actor type and actorid. Actor activation and deactivation. Dapr automatically manages the lifecycle of actors. When a message is sent to an actor, Dapr's runtime creates an instance of that actor, activates it on one of the Dapr-enabled nodes. If an actor remains idle for a configured period, Dapr automatically deactivates it, saving resources. State persistence. Actor state is automatically saved and loaded by Dapr using the configured state store component. This means even if an actor is deactivated or the host node fails, its state is preserved and restored upon reactivation. Reminders and timers. Actors can register reminders, persistent, durable alarms that fire even if the actor is deactivated, and timers, non-persistent, in-memory alarms. This allows actors to execute logic at scheduled intervals or after a delay. Location transparency. Your client application doesn't need to know which node or server an actor is currently active on. It simply requests to communicate with an actor by its actor type and actorid, and Dapr's placement service, part of the Dapr control plane, routes the message to the correct location. Concurrency management. Dapr ensures that only one method call executes on an actor instance at a time, inherently preventing race conditions within the actor's state. Benefits of Dapr actors. Simplified stateful logic. Developers can focus on the actor's behavior rather than concurrency primitives or distributed state management. Scalability. Actors are distributed across available nodes, allowing for horizontal scaling of stateful entities. Resilience. Dapr handles actor lifecycle management, including state persistence, making actors resilient to host failures. Example, an IoT device actor. Imagine an IoT device actor representing a single sensor. It could have methods like report temperature, value, update configuration, config, and activate alert. Its state would hold the device's current temperature, last reported time, configuration, and a history of alerts. When the sensor reports data, a message is sent to its specific actor ID. Dapr handles routing the message to the correct actor instance, managing its state, and ensuring the operation completes reliably. 9.2 Observability. Gaining insight into distributed applications. Understanding the behavior and performance of distributed systems is notoriously difficult. When a request spans multiple services, debugging issues or identifying performance bottlenecks can be a Herculean task. Dapr provides robust, out-of-the-box observability capabilities by automatically generating and integrating with industry-standard telemetry formats for traces, metrics, and logs. Automatic telemetry generation. When your application communicates through the Dapr sidecar, Dapr automatically emits distributed traces. Dapr sidecars automatically participate in distributed tracing. When a request passes through a Dapr sidecar, it injects trace context using standards like W3C trace context and OpenTelemetry. This allows you to visualize the entire flow of a request across multiple services and Dapr building blocks, seeing the duration of each call and identifying bottlenecks. Metrics. Dapr sidecars expose a rich set of metrics, using Prometheus exposition format, about their operations, such as request counts, error rates, latency for service invocations, state store operations, and pub/sub message processing. These metrics can be scraped by monitoring systems like Prometheus and visualized in dashboards, e.g., Grafana. Logs. Dapr sidecars generate detailed logs about their internal operations, including status, errors, and warnings. These logs provide crucial information for debugging and understanding Dapr's runtime behavior. Integration with OpenTelemetry and other systems. Dapr integrates seamlessly with OpenTelemetry, an industry standard for collecting telemetry data. This means Dapr-generated traces, metrics, and logs can be easily exported to various observability backends, including tracing backends, Jaeger, Zipkin, Azure Application Insights, Datadog, New Relic. Metrics backends, Prometheus, Azure Monitor, Datadog. Logging backends, Elk Stack, Elasticsearch, Logstash, Kibana, Grafana Loki. Configuration for observability. You configure observability by defining a Dapr configuration component or directly in environment variables. This allows you to specify the tracing exporter, e.g., Zipkin, OTLP for OpenTelemetry protocol, logging level, and whether metrics should be enabled. Example configuration for OpenTelemetry Trace Exporter. API version, dapr.io/v1 alpha 1. Kind, configuration. Metadata, name, appconfig. Spec tracing, sampling rate, 1.0. ODL, endpoint address. ODL collector observability, 4317, hash OpenTelemetry collector endpoint. Protocol, gRPC. With Dapr, getting comprehensive observability into your distributed applications goes from a complex, error-prone manual process to a straightforward, often automatic capability. This provides engineers with the necessary insights to diagnose issues quickly and maintain the health of complex systems. 9.3 Configuration. Dynamic application settings. Modern applications need to be highly configurable. Settings like database connection strings, feature flags, API keys, or logging levels often need to be changed without redeploying the entire application. While environment variables and configuration files are common, they don't inherently support dynamic updates or centralized management. The Dapr configuration building block provides a mechanism for applications to consume configuration from a Dapr-managed configuration store. This allows for dynamic updates to configuration values, ensuring your applications can adapt to changes in their environment or logic in real time. How Dapr configuration works. Define a configuration store component. You configure a Dapr component, e.g., configuration Azure App Config, configuration.kubernetes.config maps, that points to your chosen configuration store. Publish configuration. An operator or an automated process publishes configuration settings to this store. Application subscribes. Your application tells its Dapr sidecar which configuration keys it's interested in. Dynamic updates. Dapr actively monitors the configuration store. When a change occurs for a subscribed key, Dapr pushes the updated value to your application. This enables dynamic adjustments without restarting the application. HTTP API example. To subscribe to configuration keys, feature A enabled and log level from a component named appconfig store. Get HTTP localhost, Dapr port /v 1.0 configuration config store name, keys equals feature enabled, log level. Dapr will return the current values. To receive change notifications, your application would typically maintain a long-lived gRPC stream or periodically poll via the API. Benefits of Dapr configuration, dynamic updates, change application behavior without redeployment or restarts, centralized management, manage configuration for multiple services from a single source, version control for config. Configuration can be versioned and managed alongside your infrastructure. Decoupling. Your application is decoupled from the specifics of the configuration store. This building block closes the loop on externalizing key aspects of application logic, ensuring that not just data and communication are abstracted, but also the environmental settings that drive application behavior. 9.4 Chapter Summary and What's Next. This chapter explored Dapr's capabilities beyond the core building blocks, venturing into advanced patterns vital for complex distributed systems. The actor model provides a robust solution for building stateful services, making concurrent programming simpler and more resilient. Dapr's inherent observability features provide critical insights into system behavior through automatic tracing, metrics, and logging, simplifying debugging and monitoring. Finally, the configuration building block enables dynamic, centralized management of application settings, improving agility and operational efficiency. Having covered the foundational Dapr building blocks and advanced patterns, we now shift our focus to the practicalities of deploying these solutions. The next chapter will guide you through deploying Dapr-enabled applications from local development to production environments. 10. Deploying Dapr from development to production. So far, we've focused on understanding Dapr's capabilities and how to use its various building blocks. While we touched upon local Dapr init for development, the true power of Dapr shines in production environments where managing microservices at scale is critical. This chapter will walk you through the journey of deploying Dapr-enabled applications, starting from your local machine and extending to a production-ready Kubernetes cluster. The core principle remains the same. Dapr runs as a sidecar alongside your application. The deployment strategy dictates how this sidecar is injected and managed. 10.1 Local Development, the self-hosted mode. As you've already experienced, Dapr's self-hosted mode is perfect for local development and testing. How it works, Dapr init. As covered in Chapter 3, this command downloads the Dapr Runtime Dapr binary and sets up default components, redis for state/pubsub, zipkin for tracing as Docker containers. Dapr run. This command launches your application and its corresponding Dapr sidecar, Dapid, as separate processes on your local machine. Dapr run appid myapp app port 8080 path to your app. The Dapr sidecar uses the appid to identify your application. App port tells Dapr where your application is listening for incoming requests. Any Dapr component YAML files placed in the ~/ Dapr/components directory are automatically loaded by the sidecar. Advantages for development: simplicity, quick to set up and tear down, no need for a full Kubernetes cluster locally. Rapid iteration, fast feedback loop for developing and debugging Dapr-enabled features. Resource efficiency, uses fewer resources than a full cluster. Considerations for local development: production parity. While great for development, self-hosted mode doesn't perfectly replicate a production Kubernetes environment. Features like Dapr's control plane services, Sentry, placement, and MTLS are not automatically provisioned or might behave differently. Component configuration. Ensure your local component configurations, ~Dapr/components, reflect settings suitable for development, not necessarily production-grade infrastructure details. 10.2 Production deployment. Kubernetes. Kubernetes is the most common and recommended environment for deploying Dapr in production. Dapr seamlessly integrates with Kubernetes orchestration capabilities, leveraging its control plane to manage Dapr components and inject sidecars. 10.2.1 Installing Dapr to Kubernetes. Prerequisites: you need a running Kubernetes cluster, e.g., Minikube for local testing, or managed services like Azure Kubernetes Service, AKS, Amazon Elastic Kubernetes Service, EKS, or Google Kubernetes Engine, GKE. You also need kubectl configured to connect to your cluster. Install Dapr via Helm. The recommended way to install Dapr to Kubernetes is using Helm, the Kubernetes package manager. Add the Dapr Helm repository. Helm repo, add Dapr https dapr.github.io/helm-chart/. Helm repo update. Install Dapr. Helm install Dapr version DaprhlmchrtvRsion namespace Dapr system create namespace. Replace DaprhlmchrtvRsion with the latest stable version, e.g., 1.12.0. This Helm chart installs the Dapr control plane services operator, Sentry, placement, and optionally dashboard into the Dapr system namespace. These services ensure Dapr functions correctly across your cluster, providing features like automatic MTLS, service discovery, and component management. Verify installation. Kubectl get pods and Dapr system. You should see pods for Dapr operator, Dapr Sentry, and Dapr placement running, and potentially Dapr dashboard. 10.2.2 Deploying your Dapr-enabled applications to Kubernetes. Once Dapr is installed on your cluster, deploying your microservices is surprisingly straightforward. Annotation-driven sidecar injection. Dapr leverages Kubernetes annotations to automatically inject the Dapr sidecar container alongside your application container within the same pod. You add a few specific annotations to your Kubernetes pod or deployment manifest. API version, apps v1. Kind, deployment. Metadata, name, my app deployment. Spec replicas, 1. Selector, match labels, app, my app. Template, metadata, labels, app, my app. Annotations, Dapr.io/enabled : true, hash enables Dapr sidecar injection. Dapr.io/app-id : my Dapr app. Hash the unique Dapr application ID. Dapr.io/app-port : 8080. Hash the port your application listens on. Hash Dapr.io/app-protocol : HTTP. Hash, optional, if your app uses gRPC. Specify gRPC. Spec. Containers, name, my app container. Image, myregistry/myapp. Latest hash your application's container image. Ports, container port, 8080. When Kubernetes sees a pod with dapr.io/enabled:true, the Dapr sidecar injector, part of the Dapr control plane, intercepts the pod creation request. It then modifies the pod manifest to include the Dapr sidecar container and configures it to work with your application. Deploy Dapr components. Unlike self-hosted mode, where components are loaded from local files, in Kubernetes, Dapr reads component definitions from custom resources within the cluster. You deploy your Dapr components, e.g., state stores, pub/sub brokers, bindings, secret stores, as Kubernetes YAML manifests. API version, dapr.io/v1 alpha 1. Kind, component. Metadata, name. Production state store hash should match store name used by your app. Spec, type, state.azure.cosmosdb. Version, v1. Metadata, name, URL. Value, https my-cosmos-db.documents.azure.com:443/. Name, master key. Secret keyref, name, cosmosdb secret. Key, password. You apply these component YAML files using kubectl apply f component name YAML. The Dapr operator, another control plane component, watches for these component resources and makes them available to the Dapr sidecars. Advantages for production. Automatic sidecar injection. Simplifies deployment by handling the sidecar lifecycle. Built-in resilience. Dapr's control plane, Sentry, placement provides automatic MTLS, service discovery, error handling, and actor placement. Scalability. Dapr scales seamlessly with Kubernetes pods. When a pod is scaled up, its Dapr sidecar scales with it. Centralized management. Dapr components and configurations are managed as Kubernetes resources, aligning with infrastructure as code practices. Observability. Dapr's automatic OpenTelemetry integration makes it easy to plug into your existing Kubernetes monitoring stack. Common production deployment considerations. Resource limits. Define appropriate CPU and memory limits for both your application containers and Dapr sidecars to ensure stable performance and prevent resource exhaustion. Network policies. While Dapr provides application-level access control, ACLS, consider supplementing with Kubernetes network policies for broader isolation and ingress-egress control. Container image security. Ensure your Dapr runtime images, used by the sidecars, and component images are from trusted sources and regularly scanned for vulnerabilities. Upgrades. Plan for Dapr runtime and component upgrades using Helm for managing Dapr installations. High availability. Ensure your Dapr control plane services are deployed with sufficient replicas for high availability. Secrets management. Integrate Dapr's secret management with a robust secret store solution, e.g., managed cloud secret services, HashiCorp Vault, to avoid hard-coding sensitive information in component YAMLs. 10.3 Other environments and edge deployments. While Kubernetes is prevalent, Dapr also supports other deployment patterns. Azure Container Apps. This is a fully managed service that simplifies running microservices on Kubernetes without directly managing Kubernetes infrastructure. Dapr is a first-class citizen in Azure Container Apps, offering native integration and simplified deployment of Dapr-enabled microservices. You toggle Dapr features directly in the service configuration, and Azure handles the underlying Dapr runtime. Azure Spring Apps. Similarly, Dapr is integrated into Azure Spring Apps, catering specifically to Spring Boot applications. IoT Edge/Bare Metal. For edge computing or situations where Kubernetes is not suitable, Dapr can be deployed and managed using self-hosted mode running on individual hosts. This requires more manual orchestration for component deployment and Dapr sidecar management compared to Kubernetes, but it ensures Dapr's benefits are available even in constrained environments. 10.4 Upgrading Dapr. Like any software, Dapr undergoes continuous development and releases new versions with bug fixes, performance improvements, and new features. CLI and runtime. For self-hosted mode, regularly run Dapr upgrade for older CLI versions or Dapr init K for newer versions to upgrade local K8's components, or simply Dapr init to get the latest Dapr binary and default components. Kubernetes. For Kubernetes, Dapr upgrades are typically handled via Helm. You would update your Helm repository, and then use Helm upgrade to apply the new Dapr version to your Dapr system namespace. Careful planning, review of release notes, especially breaking changes, and testing in a staging environment are crucial before upgrading production Dapr instances. 10.5 Chapter Summary and What's Next. Deploying Dapr involves understanding the nuances of different environments. Self-hosted mode is ideal for rapid local development, providing a quick way to build and test Dapr features. For production-grade, scalable, and resilient microservice deployments, Kubernetes offers the most comprehensive integration, leveraging Dapr's control plane for automatic sidecar injection, MTLS, and centralized component management. Beyond Kubernetes, managed container platforms like Azure Container Apps provide seamless Dapr integration, further simplifying operations. With a solid understanding of Dapr's deployment strategies, you're now equipped to move your Dapr-enabled applications from concept to production. In the final chapters, we will explore best practices, common pitfalls, and the broader context of Dapr's role in the evolving landscape of distributed systems. 11. Beyond the basics. Best practices, troubleshooting, and community. You've now journeyed through Dapr's core concepts, explored its numerous building blocks, and understood how to deploy Dapr-enabled applications across various environments. With this knowledge, you're well equipped to start building effective distributed systems. This chapter moves beyond the mechanics, offering crucial insights into best practices for using Dapr effectively, common troubleshooting scenarios, and how to engage with the thriving Dapr community. 11.1 Best practices for using Dapr. Adopting Dapr can simplify development, but a mindful approach, coupled with best practices, ensures you reap the maximum benefits. 1. Leverage the right building block for the job. Dapr offers multiple ways to achieve similar outcomes, e.g., service invocation versus pub/sub for communication. Choose deliberately service invocation. Use for direct, synchronous request-response patterns between services where the caller expects an immediate result. Publish-subscribe. Ideal for asynchronous, event-driven scenarios where services need to react to events without direct coupling to the publisher. Promotes higher scalability and resilience. Bindings. Excellent for integrating with external systems that are not Dapr-enabled microservices, e.g., file storage, external APIs, IoT devices. Use when you want Dapr to handle the integration with a specific protocol or external resource. 2. Embrace Dapr's pluggable component model. The component model is a key strength. Infrastructure agnosticism. Never hardcode infrastructure-specific logic in your application. Always interact with Dapr's APIs, allowing Dapr to abstract the underlying implementation. Configuration as code. Manage Dapr component definitions, YAML files, in your version control system alongside your application code. This provides traceability and facilitates consistent deployments across environments. Environment-specific components. Use different Dapr component configurations for different environments, e.g., local RIDIs for development, managed Azure Cosmos DB for production, without altering application code. 3. Design for idempotency. Especially when using Dapr's pub/sub, bindings, or any asynchronous pattern, ensure your message processing logic is idempotent. This means that processing the same message multiple times produces the same result as processing it once. Dapr strives for at least once delivery, so duplicate messages can occur, particularly during retries or recovery from failures. 4. Monitor your Dapr-enabled applications and Dapr itself. Observability isn't just a Dapr feature. It's a discipline to actively engage with. Collect all telemetry. Ensure you're collecting Dapr's automatically generated traces, metrics, and logs. Integrate with your monitoring stack. Route Dapr telemetry to your central observability platforms, e.g., Prometheus/Grafana for metrics, Jaeger/Zipkin for traces, Elk Loki for logs. Dashboard Dapr metrics. Create dashboards to monitor key Dapr metrics like sidecar health, invocation counts, error rates, and component latencies. These are crucial for understanding Dapr's health and interactions. 5. Implement fine-grained access control. Prioritize security from the start. Secure by default. Consider setting Dapr's access control default action to deny to ensure that only explicitly allowed communications can take place. Least privilege. Grant each service only the minimum necessary permissions to perform its function. Define specific APIDs and operations in your Dapr access control configuration. Use secret management. Always externalize secrets into a dedicated secret store component rather than hard-coding them or putting them in application-level environment variables. 6. Think about versioning. Dapr runtime versions. Be aware of the Dapr runtime version you are using. New features, bug fixes, and sometimes breaking changes might occur between versions. Consult release notes for significant changes. Application Dapr SDK alignment. While Dapr's core APIs are stable, if you're using a Dapr SDK in your programming language, ensure its version is compatible with your Dapr runtime version. 11.2 Common troubleshooting scenarios. Even with best practices, you'll encounter situations where things don't work as expected. Knowing common culprits can save significant debugging time. 1. Dapr sidecar, not ready application, not seeing Dapr. Check Dapr run arguments, self-hosted. Ensure AppHid is unique, AppPort is correct, and the paths to your application are valid. Check Kubernetes annotations. In Kubernetes, verify dapr.io/enabled:"true", dapr.io/app-id, and dapr.io/app-port annotations are correctly applied to your deployment pod manifest. Port conflicts. Ensure no other processes are using the default Dapr ports, 3500 for HTTP, 50001 for gRPC, or the port your application expects. Dapr init status. In self-hosted, run Dapr status. In Kubernetes, check kubectl get pods and Dapr system to ensure Dapr control plane components are running. Dapr sidecar logs, the most important tool. Look at the logs of the Dapr sidecar container in your pod or the terminal where you ran Dapr run. Look for errors related to binding to ports, connecting to the control plane, or loading components. 2. Component not loading not found. Typo in component name type. Double-check the name and type fields in your Dapr component YAML against your application code and Dapr documentation. For example, pubsub Redis versus pubsub Redis. Component YAML deployment. In Kubernetes, ensure you've applied the component YAML, kubectl apply fmyComponent YAML, and that it's in the correct namespace or globally accessible, depending on scope. Metadata configuration. Verify all required metadata fields for the component type are correctly provided, e.g., Redis host, connection string. Secret store issues. If a component relies on secrets, ensure the secret store component is correctly configured and that the reference secret exists and can be accessed by Dapr. Check secret store logs for issues. Dapr sidecar logs. The sidecar logs will often show errors like component not found or failed to load component with details on why. 3. Service invocation failure/communication issues. Target AppHid correctness. Ensure the AppHid you are trying to invoke matches the AppHid parameter or Dapr annotation of the target service. Target app port correctness. Confirm the target application is actually listening on the app port specified in its Dapr configuration or annotations. Network connectivity. Check basic network connectivity between the source and target applications, e.g., ping or curl, inside the pod container if possible. Access control. If Dapr access control is enabled, ensure the calling service has permission to invoke the target method on the target service. Check Dapr control plane logs for denied requests. Timeouts retries. If the target service is slow, review Dapr's resilience configuration for timeouts and retries. Adjust if necessary. Dapr sidecar logs. Examine logs for both the calling and target Dapr sidecars. They will often show details about the invocation path, errors like connection refused or service not found. 4. Pub/sub message not delivered. Pub/sub component configuration. Verify the pub/sub name, topic, and metadata for your pub/sub component are correct. Broker connectivity. Ensure Dapr can connect to the underlying message broker. Check sidecar logs for connection errors. Subscriber endpoint. For HTTP subscribers, ensure the route specified in the subscription or /Dapr/subscribe endpoint response matches an actual listenable endpoint on your application. Application acknowledgement. Your application must return a 200 OK HTTP status for Dapr to acknowledge the message. Any other code, especially 500, indicates a message handling issue that Dapr might retry. Idempotency issues. If messages are being redelivered, ensure your application handles duplicates gracefully. 11.3 Engaging with the Dapr community. Dapr boasts a vibrant and supportive community, crucial for sharing knowledge, getting help, and contributing to its evolution. Official documentation, dapr.io, your first stop for comprehensive guides, API references, and conceptual explanations. It's actively maintained and constantly improving. GitHub repositories, Dapr/Dapr. The main runtime repository, great for bug reports, feature requests, and understanding the core code. Dapr/components contrib, where all the Dapr components reside. If you want to use a new type of state store or binding, or contribute your own, this is the place. Dapr/docs, for contributions to the documentation. Discord server. The Dapr Discord server is an active hub for real-time discussions, questions, and community support. Many Dapr maintainers and contributors are active there. Community calls. Dapr hosts regular community calls where maintainers present updates, discuss features, and address questions. These are excellent for staying up to date and engaging directly. Blog posts and talks. Follow the Dapr blog for updates and watch for Dapr talks at conferences like KubeCon, Cloud Native Con, Microsoft Build, Oz Ray Invent, which often provide deeper insights and real-world case studies. Stack Overflow, a good resource for specific coding or configuration questions. Tag your questions with Dapr. Contributing to Dapr, whether through code, documentation, or community support, helps shape its future and deepen your own understanding. 11.4 Chapter Summary and What's Next. Mastering Dapr extends beyond knowing its APIs. It involves adopting best practices that lead to more resilient, secure, and maintainable distributed applications. A proactive approach to observability and a strategic mindset when selecting building blocks are key. Furthermore, understanding common troubleshooting patterns and leveraging the helpful Dapr community will accelerate your journey. With the practical aspects covered, we'll now broaden our perspective for the final chapter. We'll reflect on the evolving landscape of distributed systems and Dapr's strategic position within it, offering an outlook on the future. 12. The future of distributed systems, where Dapr fits in. We've now traversed the landscape of Dapr, from its fundamental concepts and versatile building blocks to its practical deployment and operational best practices. You've seen how Dapr tackles the inherent complexities of distributed systems, offering a compelling solution to problems that have plagued developers for years. But Dapr is not just a tool for today. It represents a significant shift in how we approach application development in a distributed world. This final chapter will reflect on the broader trends in distributed systems and where Dapr strategically positions itself for the future. 12.1 The evolving microservices landscape. The journey from monolithic applications to microservices was driven by a need for agility, independent scaling, and technological diversity. However, this evolution unintentionally shifted complexity from within the application to the operational and communication layers. Developers, once freed from monolithic constraints, found themselves burdened with infrastructure concerns. Initially, developers tackled these complexities with specific libraries and SDKs. While effective, this approach often led to vendor lock-in, tying applications to specific cloud, provider SDKs, or proprietary libraries. Inconsistent implementations, different teams or services re-implementing similar patterns. Polyglot fragmentation, increased complexity when different programming languages involved different sets of tools. Boilerplate fatigue, developers spending more time on plumbing than on business logic. The industry then saw the rise of service meshes, like Istio and Linkerd, that addressed some of these concerns at the network layer, providing traffic management, security, and observability for inter-service communication between services. Service meshes are powerful, but they operate predominantly at layer 4.7 of the network stack and typically require applications to speak HTTP gRPC. They don't directly address application-level concerns like state management, secrets retrieval, or event publishing to heterogeneous brokers. 12.2 Dapr's unique positioning. Application mesh, or runtime abstraction. Dapr sits at an interesting intersection, bridging the gap between application code and infrastructure. Some refer to Dapr as an application mesh because it provides capabilities traditionally found in service meshes, like MTLS, retries, circuity breaking for invocation, but extends them into the application process, or more accurately, into the application's immediate sidecar scope, and provides application-level building blocks. Dapr is not a replacement for a service mesh. Instead, it complements it. A service mesh excels at transparently handling network concerns between sidecars, which Dapr's sidecars are happy to participate in. Dapr, on the other hand, excels at providing higher-level, application-focused APIs from the application to its local sidecar. Abstracting away the implementation details of various distributed system patterns and infrastructure components, e.g., specific state stores, message brokers, secret managers. This unique positioning offers a compelling value proposition: developer empowerment. Dapr puts powerful distributed primitives at the fingertips of developers through simple APIs, regardless of their chosen language or framework. Operational simplicity. By standardizing how applications interact with infrastructure, Dapr simplifies operations, debugging, and portability across different environments. Future-proofing. Decoupling application logic from infrastructure means applications are more resilient to technological changes and infrastructure shifts. 12.3 Key trends driving Dapr's relevance. Several ongoing trends in cloud-native and distributed computing amplify Dapr's importance. Distributed everything. Modern applications are inherently distributed, spanning multiple clouds, on-premises data centers, and the edge. This heterogeneity makes standardized abstractions like Dapr invaluable. Polyglot development. Teams choose the best language for their service, leading to diverse tech stacks. Dapr's language agnosticism ensures consistency across this diversity. Event-driven architectures, EDA. The shift towards EDA for greater scalability and resilience necessitates robust, standardized pub-sub mechanisms and bindings to connect disparate systems. Security and compliance. As breaches become more sophisticated, built-in security features like MTLS, fine-grained access control, and robust secret management are no longer optional. Cost optimization. Abstraction allows for easier switching between infrastructure providers, enabling organizations to optimize for cost and performance without extensive rewrites. Low-code, no-code integration. As Dapr simplifies backend concerns, it implicitly streamlines the process of integrating with front-end development, potentially fostering more productive low-code, no-code platforms that can easily consume Dapr-enabled services. 12.4 The road ahead for Dapr. Dapr is an open-source, community-driven project with a clear roadmap. We can expect to see continued evolution in several areas. More components. The community and Dapr maintainers are constantly adding new components, expanding Dapr's ecosystem integration with new databases, message brokers, cloud services, and custom enterprise systems. Enhanced capabilities. Existing building blocks will see further enhancements, performance optimizations, and more advanced features. For instance, more sophisticated querying for state management, richer pub-sub patterns, or more advanced resilience configurations. Edge computing focus. Dapr's lightweight nature and self-hosted capabilities make it well-suited for edge deployments. We might see more tools and features specifically tailored for constrained environments and intermittent connectivity. Operational tooling. Improvements in Dapr's CLI, dashboard, and integration with cloud-native operational tools will continue to make it easier to manage Dapr-enabled applications. Developer experience. Continued focus on simplifying SDKs, providing starter kits, and improving documentation to onboard new developers quickly. Wider adoption. As Dapr matures and gains more production testimonials, its adoption across various industries and cloud providers is likely to accelerate. 12.5 Final thoughts. The Dapr Way. The Dapr Way, as this book suggests, is about simplifying the journey of building distributed applications. It is not about replacing traditional development methodologies, but about streamlining them by providing a powerful, opinionated, yet flexible runtime. Dapr allows developers to focus on the business value their applications provide, rather than getting bogged down in the complexities of distributed system plumbing. It promotes portability, consistency, and resilience, enabling organizations to build future-proof applications that can adapt to changing technological landscapes and business demands. The world of software development is constantly evolving, and distributed systems are at the forefront of this evolution. Dapr stands as a testament to the power of abstraction and standardization in tackling these challenges. It empowers developers and architects to build the next generation of scalable, resilient, and manageable applications, today and in the future. As you embark on your own Dapr Way, remember that this book is a starting point. The Dapr community is a vibrant resource, and continuous learning and experimentation will be your best allies. Embrace the journey and happy Dappering.